So I'm going to change a bit notation and call our generic field K. That's because I would like to reserve the letter F to the specific Galois fields, FP, FQ, and so on. And I want to remind you the definition: a polynomial in two variables over K is a formal expression say fxy equals sum where I goes from 0 to n and j goes from 0 to, say, k, aij, x to the I, y to the j. Where we assume that the coefficient of the highest monomial, namely a and k, is non-zero. So you can write, and of course, for any I between 0 and n, and any j between 0 and k, the coefficient aij is an element of the field k. Okay, so you can I'll soon give an example, and we denote by k xy the collection of all such polynomials. Now, kxy, you can think of it as an inductive definition. I mean, we know that for any actually polynomials do not require a field as the set of coefficients, but rather you can do it everything with a ring, because polynomials, I mean, in order to add and multiply polynomials, we only need to add and multiply the coefficients, and we don't need inverse, I mean, multiplicative inverse for elements. So in fact, kxy is simply equal to, you take k and you look at polynomials in one variable over k. This is a ring. let's call it maybe R. And then you can look at polynomials over R with a new variable y. And that's kxy. Okay? So that's one thing. And of course, as a result, kxy is a ring. And you can add and multiply polynomials into variables. So this is just to set the stage. I mean, what happens in, I mean, the complexity of the theory of polynomials in two variables is far more, far bigger than the case of polynomials in one variable. One main difference is that we don't have a division with remainder for polynomials in two variables. How do we see this? Well, for a long division, if you remember, I need to have a notion of degree. And there is a natural notion of degree of a polynomial in two variables, namely the degree of f, as written here, is simply n plus k. So it's the degree of the highest monomial whose coefficient is non-zero. And I claim that we cannot have a long division in polynomials in two variables. That is, if for any f and g in kxy, we had a polynomials q and r in kxy such that I can write f as gq plus r with the degree of r strictly smaller than the degree of g. Right? That's long division. I can take fxy to be y, gxy to be x, and then if I had long division for these two polynomials, then there would exist a q and r such that y is equal to qx plus r. And the degree of r, of course, needs to be smaller than the degree of g but the degree of G is 1. So it means that the degree of R is 0. Which of course means that R is an element in the field. It's simply a constant polynomial. But then this is a polynomial equation. It needs to be true for any substitution of x and y. So I can substitute I can substitute y equals 0 and also x equals 0. And I get that R actually needs to be 0. But then I have an equation of the form y equals qx. And this cannot be possibly true for any substitutions x and y. I mean, for example, you can take I mean, of course, y is simply our notation. Y is fxy, right? So if I do f x 0, I get something that is 0. Or rather, yeah, if I take evaluating at x equals 0, we get f of 0 comma y needs to be 0, but f of 0 comma y is y, so it cannot. That's a contradiction. This is all to say, we have a much higher complexity for polynomials in two variables. And furthermore, we now have additional component in the picture, that is, we have geometry. For the field, the ground field, being the real numbers or the complex numbers, the set of all solutions let's say of fxy equals 0, the solution set, I remind you, is the set of all let's say x0 y0, such that if you substitute it in the polynomial, if you substitute it in the polynomial, you actually get 0. And the solution set of of a polynomial over the real numbers, for example, it has a geometry. For example, you take fxy equals y minus x squared. Let's say over r. Then I can picture the solution set of f. This is simply the set of all xy in the plane r squared, such that y minus or y equals x squared. So this is a parabola. Okay, and this is in sharp contrast to the solution set of a polynomial in one variable, because we know that a polynomial in one variable can have at most n distinct roots, where n is the degree. So we cannot possibly expect any meaningful geometry. And what happened historically with, I mean, how did mathematicians get into elliptic curves? So historically it was Diophantus, who studied integer solutions to various polynomial equations. So you can, I mean, the first example is an equation of the form ax plus by equals c. Let's say a, b, and c. Maybe I should write g. A, b, and g are integers. We'll find all integer solutions to this equation. So if you remember, we talked about it when we did some elementary number theory. This is called, I mean, solutions x and y to this equation are the so-called Bezout coefficients. And they exist if and only if G is the GCD of A and B. But typically they are not unique. There are many Bezout coefficients for a given triple or a given pair A and B. And there is a method, modernly you do it with an integer version of Gauss elimination, for those of you who know. There is a simple method, and also Diophantus apparently knew of a simple method to find all the possible integer solutions to this equation. So this is solutions for polynomial in two variables of degree 1. And the next thing to look for is polynomials of I mean, in two variables of degree 2. And I will not get into the details, but it turns out that you can also study, I mean, you can also completely classify the solution, integer solution for polynomials in two variables. Sorry, in two variables of degree 2. And then the next thing to look at is degree 3 polynomials. So degree 3 polynomials have the general form let's say ax cube plus bx square y plus cxy square plus dy cube plus ex square plus fxy plus gy square plus hx plus iy plus some free coefficient j equals 0. And here the complexity is much more significant than in degree 1 and 2. And Diofanto started to study. I mean, this was the place where he kind of got stuck. I mean, he did have some insights, but it was apparent to him and to later mathematicians like Euler and Hilbert that you actually need theory to deal with this case. And I mean, over the years, in order to simplify, you can do this is true also in degree 1 and 2. I mean, you can do a change of variables. So, for example, so to simplify, let's say you have ax plus by equals c. You can do, let me just pick up the details here. Let's say that b is non-zero. Then I can write it as y equals minus a over b x plus minus c over b as a, or rather, well, okay, let's say plus minus c over b. And this is the familiar form of a line. I mean, you call this guy m and this guy b, or maybe b prime, and you get y equals mx plus b prime. And you can do similar substitutions in degree 2 to get into, well, in degree 2 and also in degree 3. In degree 3, the substitutions lead you to, so in degree 3, yes?
There shouldn't be minus before the second term, or should it?
Because we have ax plus by, so
Before
yes,
c divided by b.
Yeah. I think, yeah, you're right. Thanks. Yeah. But okay, so in degree 3, I will not give you the details, but it can be found. Some of it is in the notes, and other you can look in the web. In degree 3, the first simplification it gives you an equation of the form y squared plus a1 xy plus a3 y equals x cubed plus a2 x squared plus a4 x plus a6. And this is called the generalized Weierstrass form. So degree 3, by the way, is called degree 3 polynomial in 2 variables is called a cubic. So by a change of variables, I can turn any cubic into a generalized Weierstrass form. And of course, since I only care about, we only study solutions for these equations, the change of variables is, I mean, does not change the set of solutions. So we're not losing any generality in this change of variables. And it turns out that if the characteristic of K is not 2 or 3, then there is a further a simplification to the form y squared equals x cubed plus ax plus b. Okay, so an elliptic curve over a field K is an equation of the form E is y squared equals x cubed plus ax plus b, where of course the a and b are scalars in the ground field K. Here we also denote E over K. So one thing to notice in the definition is that elliptic curve comes kind of equipped with a declaration over which field it is defined over. Because of course you could have, I mean, if let's say K prime is a field containing K, field extension. We can consider the same equation, but over the larger field K prime. And this will be for us in the formal aspect, it will be a different elliptic curve, even though it is the same equation, the same coefficients, everything. But if it is defined over a different field, we consider it as a different object. And the reason is that, again, we are interested in the solution set, and the solution set of this equation over K prime is typically will be different than the solution set over K. I mean, namely, because K prime has more points, then there will be an inclusion. I mean, the solution set over K will be a subset of the solution set over K prime. Okay, so an elliptic curve is you always have to specify over which field you are considering it, and you have this equation that, as we said, this can be simplified from the generalized Weierstrass form. If we have a characteristic different than 2 or 3, and I didn't finish the definition. The additional condition is that the quantity 4a cubed plus 27b squared is non-zero. Okay, so that's the definition of an elliptic curve. Let me just, I mean, henceforth, we simply assume that all our fields have a characteristic that is not 2 or 3. And this covers the vast majority of cryptographic applications. I mean, typically, we take, I mean, in cryptography, we take an elliptic curve defined over Fp, where P is a very large prime, let's say 200 digits or something like that. So it is very safe to assume that the characteristic is not 2 or 3. There are applications in cryptography in which people work with the characteristic 2 or 3. There are not many of them, and they have a security issue. There are specific attacks that work in this characteristic. So for us, it will be convenient to simply assume we work in characteristic that is not 2 or 3, because the equation is much more convenient, and as a result, all the stuff we build on it, all the calculations and so on, will be simpler. Any questions so far?
Maybe one question. When we went from generalized Weierstrass form to simplified, we had x and y in the generalized and x and y in the simplified. But I guess these are like different x and y's, right?
Yeah, you do a change of variables. I mean, you replace x. Again, for simplicity, I just use the same notation. But if you want to be formal, you can call these guys, for example, x prime, y prime.
Yeah. Okay. Okay. That's all.
Yeah, and this, by the way, this thing is called the short Weierstrass form. Okay, so we will focus on the short Weierstrass form, and the next thing in order is to explain this strange condition, right? This is called the discriminant delta, and it is analogous to what you know from high school as the discriminant of a quadratic polynomial in one variable. Okay, so but before we go into this condition, let's draw something. So typically, say over R, the elliptic curve will look like this. My drawing skills are limited, but it should be something like this. Like this fish, and sometimes it could have another part of the curve being this lake. So you see, of course, this you can see algebraically the equation y squared equals x cubed plus ax plus b. This is symmetric along the x-axis, right? I mean, for every x, we possibly, I mean, we have exactly. I mean, if we have a solution y, then also minus y is a solution. So we have symmetry along the x-axis, and these are the intersections of the polynomial x cubed plus ax plus b with the x-axis, and there is a proposition. It's not hard to see that over the real numbers, polynomial in one variable of degree 3 can either have one root or three roots, but it cannot have two roots. So either we have this this full picture of the fish in the lake, or we have only the fish. Okay, and of course you can. I mean, you can do a translation of the graph and so on, but we don't care that much about all these change of variables. We have this canonical Weierstrass form. So, okay, so this is the picture, and the main theme of well, at least one major way to reason about elliptic curves, at least in the early stages, is to use the geometry over R and to deduce something about the elliptic curve when it is defined over a finite field. So another warning. Take, for example, the elliptic curve y square equals x cubed plus 2x plus 3. And let's say over the real numbers. I could think of, we could consider some large prime P, and look at the equation, the same equation, E, but now over FP. So this will be, again, y square equals x cubed plus 2x plus 3. And let's suppose that over R, I didn't check it, but it's just one of these, one of these cases. So for simplicity, let's suppose it only has the fish component. And now one thing you could maybe try, I mean, of course, if P is large, then you could try to simply plot the solution set of this equation in a discrete manner, right? This would be P minus 1 and so on. This would be 1, and you do the same in the y-axis, and you plot the graph. I mean, sorry, the discrete version of the solution set over FP. It would not by any means be a discrete version, I mean, some discrete subset of the graph of E over R. Not in any, I mean, not even remotely. Can anybody say why? I mean, how come? I simply took a subset. A subset FP is a subset of R. And I looked at all solutions. I mean, here the graph was the set of, I mean, here the graph was the set of all solutions to this equation. Now I look at the set of all solutions. Why don't I get something like this?
I want to say something related to subfields, but
yeah, so say.
I mean, if we can assume that FP is a subset of all the real numbers, everything that it's close, I mean, it will share at least from 0 to P, all of the values, right? So according to the image that you show, all of the values between 0 and p should still be a straight line. Once you arrive to p, you have the modulo, so you get back. And at the end, you cannot have a drawing that it's just dotted lines.
So the reason is that the solution set highly depends on the arithmetic of the field that we work over, right? And FP is indeed a subset of the real numbers, but it's not a subfield. I mean, the arithmetic on FP is not induced by the arithmetic of the real numbers. So the solution set is completely different. Okay, and
I don't know.
yes, Lisa?
But if it will be another function, another equation that on real numbers is defined exactly on the same, like if it is defined exactly on the FP of R, like on FP area of R, then it will be the same.
I'm not sure I understand the question. I mean, the issue is, of course, if all the values of x cube and y square are smaller than p. I mean, if you take xy such that both x, y, x cube and y square, and also x cube plus 2x and x cube plus 2x plus 3 are all smaller than p, then the arithmetic is the same as the arithmetic of R, and this will be a subset.
Yeah, this is my question.
Okay, but of course, once you go, typically once you take high values of x, then x cube is in FP. I mean, x cube is not the same as x cube in R. So it will be different, right? I mean, you can if you want, the same principle, of course, works for any prime number. So take p equals 5. P equals 5. Once you do, I mean, once you take x to be even 2, then x cube is going to be 8, which modulo 5 is 3. So it's not going to be, I mean, it's not the same arithmetic as taking x cube as a real number. Okay, and typically, and that's really the heart of the difficulty. I mean, typically, over a field of finite characteristic, we don't have any geometry. I mean, sure, you could arrange the numbers 1 up to p minus 1 in the x-axis, in the y-axis, but you will not get this nice picture of a fish or a fish in the lake, and so on. You will get, you can try to plot it for large primes. You will get some junk. I mean, there is no nobody, at least until now, was able to make sense of the geometry if you try to plot the solutions of an elliptic curve over a finite field. So a main theme in the study of elliptic curves is to use analogies. That is, I have the intuition of geometry from the elliptic curves of the over the real numbers, and with this geometry I could do different constructions, like I could look at the tangent line. And now when I work over a finite field, it turns out that a lot of the constructions, like the tangent line, make sense over any finite field. So I simply call them the tangent line, even though there is no real geometry for which this is a tangent line. Okay? So this kind of a method of reasoning is called algebraic geometry. Yes.
Would FP be called the base field of the elliptic curve?
Yes, we say that the elliptic curve is defined over. I mean, it's kind of in your declaration. You need to declare over which field your elliptic curve is defined.
Yeah,
it's a bit like a function. You need to declare what is the domain and the range. What is the input set and the output set? Like in a typed programming language, when you write a function, you have to declare what is the type of the input and what is the type of the output. And if you declare different input type and output types, it's formally speaking, it's a different function.
thank you.
Okay, so this kind of reasoning is algebraic, is generally called algebraic geometry. Algebraic geometry studies solution sets of polynomials in, I mean, typically in many variables. Polynomials in two variables, I mean, the solution set of polynomials in two variables result into a one-dimensional graph. That's the reason for the name curve. Of course, the one-dimensional graph, depending on the degree of the two-variable polynomial, the one-dimensional graph could have a different shape. And what people do in algebraic geometry, I mean, they study, for example, if you take polynomial in 3 variables and you look at the solution set, then you have like 2 degrees of freedom. I mean, right? If you have a polynomial in 2 variables and 1 equation, then you have 1 degree of freedom. So that's why you get 1 dimension. If you have three variables, you have 2 degrees of freedom, so you get surface. And in general, polynomial in n variables, I mean, the solution set of polynomial in n variables will be an n-1 dimensional, it's called a variety. And I mean, just like I mentioned here, with this, I mean, the geometry over R can serve as analogy for constructions over a finite field. This is something typically people do in algebraic geometry a lot. But so from the perspective of algebraic geometry, we are on the gross level. We study the one-dimensional, I mean, basically the simplest object. It's like curves, one-dimensional varieties. But as you will see, it's still a very rich object, and we will use a little bit of tools from algebraic geometry, but I will not get into the actual theory. So maybe it's a good time to take a break, and after that I want to come back to this condition on the discriminant.
10 minutes, madam, as usual?
Yeah. Yeah.
Okay, cool.
Okay, can we start again?
Yep.
All right. So remember, we have the typical equation y squared equals x cubed plus ax plus b. And we said that an elliptic curve is such an equation with the condition that for a cube, sorry, yeah, for a cube plus 27b squared is non-zero. By the way, I will often denote the elliptic curve as EAB. So this is a short notation to talk about the parameters A and B. Now, suppose you have a suppose fxy is an equation over the real numbers. A tangent line to f, or to the graph of f, to be precise, at a point in the graph, so at x0, y0, I mean, such that f of x0, y0 is equal to 0, is given by let me denote it as t x0, y0. This is an equation of the form y minus y0 equals m x minus x0, where m is the derivative of y with respect to x at the point x0, y0. Now, the tangent line, yes.
I have one question. So the tangent line is going to be a straight line, if I'm not mistaken.
Yeah, it's a straight line.
So in regards of that, depending on the point where you are doing the tangent, or maybe not even depending, this line will collide twice with the curve. Or could collide with the curve, at least. I don't know.
Yeah, yeah, it will intersect, but a tangent at a point. Let's take the example of an elliptic curve. Let's say you do tangent here. This is x0, y0.
Yeah.
So it is true that the tangent will intersect the elliptic curve in at least another point, possibly even further if you have this lake, right? but a tangent means that there is a neighborhood, let's say on the x-axis, around x0, for which if you take the part of the graph above the neighborhood, the line intersects the curve in exactly one point in this neighborhood.
Okay. And like, so how can I say that? I mean, what does this imply in the sense of, because the neighborhood just appeared now, but I'm wondering in respect to the solutions to the polynomial and all this kind of stuff, does it have any effects that this tangent line collides in two places? It doesn't really matter for anything.
It doesn't matter as long as we, again, we are interested in the property that it touches the curve in exactly one point in some neighborhood around the point x0, y0. And it's true, it may intersect the curve in other points, but it's this kind of intersection in x0, y0 is of a special characteristic, right? It's just like you know, you have a parabola, then the line that is tangent to the base of the parabola, or even the line that is tangent here, has different characteristics than a line that simply intersects the parabola. Right? This kind of line, the tangent line, you can take the slope. This is let's call this angle alpha, then tangent alpha is what we denote as the slope, and m is as I said, it's the derivative of the function with respect to the variable x, and it has special characteristics precisely because of the relation between the slope and the derivative. Okay, so it's like it's a line that touches the graph of the function but does not intersect it. I mean, it may intersect it in a later, right? But in some neighborhood, let me maybe draw it again. In a parabola, you take a point, and this is x0, this is x0, y0. And you take the tangent line, then it touches the graph of the function in exactly one point, but it's either outside of the graph or inside, but it's not in both sides. I don't know if that
yeah, that explains it well. Yeah. Thank you very much.
So it's like just like for a circle, there is a difference between there is a different characteristic between the tangent line to a circle and simply a line that a generic line intersects the circle in 2 points. But the issue is not the number of intersection points, but rather that the line is is completely on one side, either inside or outside. But okay, so this is the tangent line. It's we have an equation for it. I'm not going to develop it completely. This is something you typically do in high school mathematics. But for us, okay, so we have a tangent line for any graph of a function if the derivative exists. But we are dealing with polynomials. For polynomials, the derivative is very easy to calculate. I mean, unless you're dividing. I mean, unless the derivative ends up in a formula that, I mean, when you substitute x0, y0, you suddenly divide by 0, then the derivative always exists. And my first claim is that the condition on the discriminant. So let me be formal. Suppose E over R is an equation of the form y squared equals x cubed plus ax plus b. Then E is an elliptic curve I mean, elliptic curve, of course, it means that in addition to the equation, we have this discriminant being non-zero. If and only if, for every point x0, y0 on E, there is a well-defined tangent line. And just to give you an example of kind of a non-example, when the tangent line does not is not defined uniquely, an example. You take, let's say, y equals x cubed. Then this is something like this. And the tangent line, or maybe this it will answer your question, Carlos, a bit better. Why in this case we don't have a well-defined tangent line? I mean, I would typically want to take the tangent line to be the purple, let's say it's 0. I mean, x0, y0 equals 0, 0. And I mean, I would want, if I had a tangent line in this case, then I would expect it to be the purple line. But I mean, one property that I expect from tangent line is a kind of continuity. So if I take the tangent line at this point, and then I take the tangent line at this point, and I get closer to 0, then I mean I get right. Then I get this tangent line here, but on the other hand, if I do it from this direction, then I get the blue line. So one property that I demand from tangent lines is that if I kind of take a family of tangent lines at points getting closer and closer to x0 y0, then I get kind of a sequence of tangent lines that converges to the resulting tangent line at x0 y0. Yes.
I mean, from like if I analyze what you just did from the limits perspective, like if you were doing a limit from one side and from the other one and getting close to 0, you will end up in the same value if you go from both sides. But in the case that you did now, which is taking the tangent line at points that are closer to 0 coming from one side and the other one, how can you end up with different axis lines? Like how is that from the right you get
actually
the purple and the blue from the other one?
Yeah. Sorry, I got a bit confused. I think let me take it back. I do not get the blue.
I'm not correcting you in any sense.
No,
I have
no.
clue about that.
No.
Just
But
a
you are right to. The issue here is, I mean, this is not considered a tangent line. I mean, we do have the derivative. Okay, but you know what? Let me take it back. I mean, what I want in the case of elliptic curves. Let me take back the non-example for now, because I don't want to get you into this calculus issues of limits and so on. It's too complicated, I think, for our purposes. But well, okay. You will see in the proof of the proposition what I mean by a well-defined tangent line.
Okay.
Okay.
Fair enough.
So of course, we can write y equals plus minus square root of x cubed plus ax plus b. And so it has two parts, right? I mean, in this example, it would be like the first half, and then the second half. Okay, and each of these is an ordinary function. I mean, it's an ordinary function in one variable. So I could think of it as y equals y of x. It's a function of x. And when y is non-zero, then I can simply take the derivative then a dy to dx is going to be plus minus 3x squared plus a over 2 square root of x cubed plus ax plus b equals 0, right? So okay, so I need to correct. Sorry, this m is not. I apologize. This I did it a bit fast. So going back to the definition, the tangent line is a line that passes through the point x0, y0, and is given by this equation. M is the slope of the tangent line t. And what I know, I mean, in the tangent line is that the derivative okay, so in this case where y is non-zero, then I want the derivative of y with respect to x to be 0. And this happens if and only if, I mean, this equation is satisfied. And then we will have a well-defined tangent line. If so we will have a well-defined tangent line in order to have a well-defined tangent line, I need that x cubed plus ax plus b is bigger than 0. Yes.
Do we need any quadratic residue properties? Like, how can we be sure that the square root of this number exists within the field?
So as long as it is positive, then the square root exists. Now, okay, so now if x cubed plus ax plus b is negative, then there is no point on the elliptic curve for which the
But then positive or negative here might just be a convention, right? Because we are in a cyclic Like we're in a prime field where we have a modulus and we go from 0 to p. So
No,
all
no,
power values are positive.
No, the entire proposition is over the real numbers.
Oh, fair enough. Okay, apologies.
So if the expression x cubed plus ax plus b is bigger than 0, or even if it's bigger than 0, then the square root exists, and this expression here in the box is meaningful. I mean, I'm dividing by 2 times the square root of something, and this something is non-zero. If this expression is negative, then there is no xy on E with this value, because remember, to be a point on the curve, you need to satisfy y square equals x cubed plus ax plus b. If this thing is negative, negative, then it cannot be y square. I mean, of any y, right? Because y square is always non-negative. So this case we can ignore. And then we are left with the case of x cubed plus ax plus b equals 0. And here we need to take a slightly different approach. We do implicit differentiation. And with this implicit differentiation, we take, we simply derive the equation y square equals x cubed plus ax plus b with respect to x. So we do d of dx. And what we get is d of y square dx equals, I mean, here you do 2y times dy dx. And of course, if you do d of x cubed plus ax plus b with respect to x, then you get a 3x squared plus a. So what we get is that 2y dy dx equals 3x squared plus a. Or in other words, dy to dx is 3x squared plus a over 2y. So, okay, so now we analyze this expression. Suppose y is equal to 0. But 3x squared plus a is non-zero. Yeah, so if y is equal to 0, then this expression is not really defined, because I would need to divide by 0. But I could do we can interchange the roles of the variables x and y, so that the numerator is 0 and the denominator is non-zero. So this means that the slope is after we interchange between x and y, dy to dx, which is the slope, is so the slope will be 0, and then I can interchange again we get a tangent line parallel to the y-axis. So the picture here is really, I mean, if y equals 0, but this expression 3x squared plus a is non-zero, then this is in fact the point here, or it could be one of the points here. And in each of the cases, we have a tangent line that is parallel to the y-axis. I mean, the slope is kind of infinity, but the tangent line is well defined. And then finally, I need to take care of the case where y equals 0 and 3x squared plus a is also equal 0. If y equals 0 and 3x squared plus a equals 0, then necessarily a is a negative number, right? I mean, a equals minus 3x squared. So we substitute instead of a, I substitute minus a to get. So now the equation looks as y squared equals x cubed minus ax plus b, with and now a is a positive number. In that case, three x squared minus a equal to 0 implies x equals to plus minus square root of a over 3. Now, I can substitute it. So I have this equation. Let's call it star. Substituting that in star gives us the following. I have, let's say I substitute a plus square root of a over 3 instead of x. And I know that y is equal to 0. So I get that square root of a over 3 cube minus a square root of a over 3 plus b is equal to 0. That's the equation that that comes from the fact that we assume that xy is a point on the curve. And this is equivalent to simply saying a 2a 3 over 2 divided by 3 square root of 3 equals b. And from here, I simply get a 4a cube over 27 equals b squared. This is simply by exponentiation of the previous equation. And now I get 4a cube minus 27 b squared equals 0. When I substitute back again a equals minus a, I get that this is equivalent to 4a cube plus 27 b squared equals 0. So we have a we have a well-defined tangent line at this point, if and only if delta is non-zero. So this is okay. I think it was a bit of a mess, but I wanted to kind of give you at least the intuition of where this, the geometric intuition of where this this condition comes from. So what it means geometrically, at least over R, is that I mean, we can talk about the tangent line at every point, and it will be a well-defined, I mean, a well-defined notion coming from the equation coming from this equation written here, and m needs to be the derivative at the point, but it has to be non-zero. otherwise we get well, a degenerate version. So when I divide into all the cases and so on, what I get is that I need this condition, delta being non-zero, in order to have tangent lines defined at all points. Any questions about this proposition?
Is there a link between this and the characteristic not being equal to 2 or 3?
So the characteristic not being 2 or 3 is simply because we want the short Weierstrass form instead of the general Weierstrass form.
Yeah, okay. So there's no link. Thank you.
In a way, you could say it is affected because when you do Mark.
Yeah. If we had characteristic 2 or 3, we wouldn't have the short Weierstrass, and so we wouldn't have had the same equation at the end.
Yeah, but also delta would be different. I mean, delta depends on the type of the equation.
Yeah.
So in general, Weierstrass form, a delta of E is defined differently. But still, if you would like to define elliptic curve in a general Weierstrass form, then once you know what is the formula for the discriminant of your equation, then your condition would be that the discriminant is non-zero.
Mm-hmm. Thank you.
So this is the geometric intuition between for the condition of the discriminant being non-zero, and I want to finish today's session by the algebraic interpretation of this condition on the discriminant, and this is the last proposition, which is true actually for all the fields we care about. So let K be either the field of real numbers or a field of positive characteristic that is different than 2 or 3, right? A cubic fx equals x cubed plus ax plus b over k admits a repeated root over k bar if and only if the discriminant is non-zero. Discriminant, again, let me just remind you. This is 4a cubed plus 27b squared. And this needs to be non-zero.
So in another way of saying, the polynomial, cubic polynomial has 3 distinct roots if the discriminant is not 0. Correct.
Exactly. So this is analogous, if you remember from high school, when you have a quadratic ax squared plus bx plus c, then somehow in the solution formula you have a square root of the discriminant or something like that, right? And so you have plus minus. I mean, I don't want to write the whole formula, but the discriminant in this case would be what is it? I already forgot, but b squared.
B squared minus 4ac.
B squared minus 4ac. And of course, you have simply no minus or plus, I forgot.
Minus.
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 So, of course, you have no solution if the discriminant is negative, because then you cannot take, you have no real solution. You cannot take a square root of negative, but you will have complex solutions. But you can ask, okay, I mean, the algebraic closure of the real numbers is the complex numbers. So I can always, I can always look for solutions of this quadratic over the complex numbers. And what I want to know, at least sometimes, is when do I have repeated complex root? Repeated complex root exists if and only if the discriminant is exactly equal to 0, because then the plus minus cases coincide. And what I'm saying is that the discriminant that we have here has the same property. So I take any field that is not, I mean, either the real numbers or one of our finite characteristic fields, and I look for all the roots over the algebraic closure. So over the algebraic closure, I have exactly 3 roots, but possibly with repetitions. And the condition that delta is non-zero is completely equivalent to the condition that when I look at the roots in the algebraic closure, then I have no repetition. Okay, is this the statement of the proposition clear? All right. So the proof is very simple. Over k bar, we can write fx equals x minus alpha 1, x minus alpha 2, x minus alpha 3. But of course, this is also equal to x cubed plus ax plus b. So I can open up and I get 3 equations. One of the equations, this you'd have to believe me for now, but you can do it in your spare time. One of the equation is the equation for the coefficient of x squared. The coefficient of x squared is alpha 1 plus alpha 2 plus alpha 3, and this has to be 0. Then the coefficient of x in this right-hand side expression is alpha 1 alpha 2 plus alpha 1 alpha 3 plus alpha 2, alpha 3 equals A. And the last equation is alpha 1, alpha 2, alpha 3 equals minus B. Okay, so if F had a repeated root, let's say that alpha 1 is equal to alpha 2. So I will denote both of them as alpha. Then I can simply write the third root, alpha 3, is minus 2 alpha. Yes?
Sorry, maybe I missed this step. I don't understand. How do you come towards thinking alpha 1 plus alpha 2 plus alpha 4 equals 0? I don't see the link between the line before and this one.
I mean, I have the right-hand side, and I know that it must be equal to the left-hand side.
Yep.
So I open up the right-hand side, and this is an equation of two polynomials. Equation of two polynomials means that the coefficient of all the monomials are equal.
Okay, so you just expand all the monomials at the right-hand side and say, because there's no x square, then it must be equal to 0 or something like this.
Yes, exactly.
Okay.
I mean, I'm a bit short of on time, so I'm
yeah, I understand. No worries.
I'm
I get it.
skipping, but it's straightforward.
Yep. Thanks.
Okay, so we conclude that alpha 3 is minus 2 alpha, and then I can substitute it back to this system of equations, and I get that A is equal to alpha square minus 2 alpha square minus 2 alpha square, which is minus 3 alpha square. And I also get that B is equal to minus 2 alpha cube. Okay, so that's my system now. And I can exponentiate. I want to get rid of the alpha. So I exponentiate the first equation by 3 and the second equation by 2. So I get A cube equals minus 27 alpha to the 6, and a B square equals 4 alpha to the 6. And now I can simply divide the first equation by the second equation, and I get A cube over B square equals minus 27 over 4, which is of course equivalent to simply say that 4A cube plus 27B square equals 0. So if there are repeated roots, repeated roots of fx equals x cube plus ax plus b in k bar, then the discriminant is 0. And if the discriminant is non-zero, then I cannot possibly have repeated roots, because that's I mean, our reasoning led us to see that if you have repeated roots, you cannot have. So if the discriminant is non-zero, there are no repeated roots. Okay, so that's the proof. You can fill in the details. It's also in the notes. But basically, what I want you to take from this session is that the condition of the discriminant being non-zero in the definition of elliptic curves has two justifications, if you wish. One justification is the geometry, and that's we want a tangent line to be well defined in all points. And the second one is algebraic, and this is the fact that this polynomial does not have repeated roots in the algebraic closure. Questions, requests for next time?
It's maybe not a question, I don't know, but like I'm a bit confused with the tricks you use. I mean, when it's not like maybe like specifically here, but in general, like when we substitute whatever we want by whatever we want, and like okay, if that I understand, but here like when we just like take to the third power and to the second power something just because we want to take it to some power, it feels like there should be some reasoning why we are allowed to do that.
Well, I mean, the reason for why we are allowed to do it is because it's the basic rules of algebra. I mean, you have an equation. If the left-hand side is equal to the right-hand side, then you can exponentiate it at any exponent. If you exponent the right-hand side and the left-hand side, then you must get still an equation, an equality. But the reason that we specifically did exponentiation here is that we want to cancel out the alpha, and the only way,
it makes sense.
The only way to cancel out the alpha is to have alpha of the same power in both, you know, in the first equation and in the second equation. Then I can divide.
And it doesn't matter that we, for example, can't go back from this exponentiation.
All I wanted to, I mean, what I wanted to reach is that if I have a repeated root, then the discriminant is 0, and vice versa. But that's easy. I mean, what I wanted here is that if I have a repeated root, you should think of it as a chain of reasonings. So I start like with the assumption of I have a repeated root. I write all the equations, and then I manipulate them in a way so that I get an expression depending only on the coefficients of the original polynomial, and not depending on the roots themselves, alpha and alpha 1, alpha 2. Okay, that's kind of the goal that I wanted. I wanted to reach a condition for whether I have repeated roots or not, only using the coefficients of the original polynomial, and not depending on the specific properties of the roots.
Makes sense.
But in general, I mean, what we had in the maybe in the first part of this session, there are different substitutions that lead you to simplifying the equations. This took mathematicians many years to discover, and so you should think of it as kind of we now know how to do it. So we have, I mean, we can teach it very quickly, but to actually think about it, this requires a lot of effort.
Okay, got it.
There was another question from Ox, maybe?
No, I was just trying to say the reason we could divide those two equations because we are trying to eliminate alpha 2 and in what condition, what relation that alpha will gone away. That's what I was saying.
Yeah. So we are interested in a condition depending only on the coefficients a and b, and not on the roots alpha, because we don't have access to. Typically, we don't have access to the roots alpha 1, alpha 2, and alpha 3. We have access to the original coefficients. Okay, so let's stop here and we continue next time.